Let's use our new way of thinking about definite integrals to solve a problem closely related to finding an area between functions of x. And that's to find the area between two functions of y. So let's find the area enclosed by this parabola, x equals minus y squared plus 4y minus 3, and the x-axis. To get a handle on what this all looks like, let's sketch a graph of this. We're going to need to know where this parabola intersects the y-axis. So the y-axis is where x is equal to 0. So let's just take our parabola and set x equal to 0 in that equation so that we can find the intersection points. So 0 equals negative y squared plus 4y minus 3. Let's, I don't know, multiply both sides by minus 1. That gives us 0 equals y squared minus 4y plus 3. And now I see this factors. So this is y minus 3 times y minus 1. So if we graph this, it looks like this parabola is going to go through the y-axis at y equals 1 and at y equals 3. And because of the minus sign in the front of this parabola, it opens in the negative x direction. So that's going to look something like this. So the region that we want is this bump that's sticking out to the right of the y-axis. I guess one way to figure out what this area is would be to slice it up vertically. But, this is a parabola. It's sort of naturally, the way this parabola is facing, it's sort of naturally written as a function of y instead of a function of x. So if we sliced this into vertical strips, that's really describing things in terms of x. But, we'd rather express things in terms of y in this case, just because that's sort of more natural. So let's see if we can decompose this area into horizontal strips instead of vertical strips. So for every y value, there's a horizontal strip in this region. And this horizontal strip is so narrow, top to bottom, that it's essentially a rectangle. And so the area of one of these strips is just the width times the height. But the height is infinitely small. The height is an infinitely small distance in the y direction. So the height we can express as dy. Remember, d of a variable is how you express an infinitely small bit of that variable. So now we just need to write down what is the width here. But the width is just the y coordinate of this right-hand point. I'm sorry, the x-coordinate of this right-hand point. But that's exactly what the equation for the parabola tells us. So this width is minus y squared plus 4y minus 3. So this is the area of one of these strips. Of course, there are infinitely many of these strips, one for every y value. And so to add up all of these areas, we just need to integrate this infinitely small area. So the total area, and this is unsigned area, the total area is the integral. So there's one of these strips for every y value from 1 to 3. So our integral should have y bounds from 1 to 3. And the area, the infinitely small area of the strip that we're integrating is minus y squared plus 4y minus 3 dy. All right. So you can see that this is very similar to the area of, or how we found the area of a region by splitting it up into vertical strips like this. But we're just treating y as the independent variable instead of x. But it's the same general idea. Now that we have this integral written down, we can go ahead and evaluate it. So let's see, writing down an antiderivative, we get negative 1/3 y cubed plus 2y squared minus 3y. And we need to evaluate at 1 and 3. So evaluating at 3, we get negative 1/3 times 3 cubed plus 2 times 3 squared is 9 minus 3 times 3. Okay, and then we need to subtract and then plug in 1. So minus 1/3 times 1 plus 2 times 1 minus 3 times 1. So let's see. 3 cubed times a third is 3 squared. 3 squared is 9, so minus 9 plus 2 times 9 is 18, minus 9, minus negative a third, let's see, 2 minus 3 is minus 1, minus another third is minus 4 thirds. All of these first integer parts, these all cancel, or add up to 0, and so we get 4 thirds. So the total area to the, between this bump and the y-axis is 4 thirds.